Hi, this is Patrick Bobolt from Kellogg Community College, and I'll be teaching you Lesson 3.2, the derivative of a function. The definition of a derivative is the derivative of the function f of x with respect to the variable x is the function f prime, whose value at x is f prime of x, which equals limit as h approaches 0 of f x plus h minus f of x all over h. The alternative formula for the derivative is f prime of x equals limit as z approaches x of limit of f of z minus f of x all over z minus x at the points z, f of z, and x, f of x. And those are just 2 points off of the function. The process of calculating derivative is called differentiation. Notations for differentiation of the function y equals f prime of x, f of x, is f prime equals f prime of x, which equals y prime, which equals dy dx, which equals df dx, which equals ddx of f of x, which equals dfx, which equals dx fx. And dy dx is just the differentiation of the function of y in terms of x. Df dx is differentiation of the function with respect to x. And d dx of f of x is differentiation of x of f of x. D dx and d are called differential operators. To indicate the value of a derivative at a specified number x equals a, you get f prime of a equals dy dx at the number x equals a, df dx at the number x equals a, which is also d dx of f of x at x equals a. What we learned from the graph y equals f prime of x, where the rate of change of f is positive, negative, or 0. 2. The rough size of the growth rate at any x and its size in relation to the size of f of x. And 3. Where the rate of change itself is increasing or decreasing. An example we have is the ddx, or derivative, of mx plus b equals the limit as h approaches 0 of mx plus h plus b minus mx plus b. And that's just in the form of our f of x plus h minus f of x. And then if we distribute it out, we would get mx plus mh plus b minus mx minus b. And we can see that the mx and our b's are going to cancel. So then we're left with the limit as h approaches 0 of mh over h. And now our h's are going to cancel. And we're just left with limit as h approaches 0 is m. And since there are no h's, it does not approach 0 anywhere, so it's just m. A function only has a derivative at a point if it has left hand and right hand derivatives there. And those one-sided derivatives are equal. So our ddx of mx plus b equals m, and our ddx of the square root of x equals 1 over the 2 square root of x. And we can find this by doing the same thing as we did here, and we'll come out with that. When a function does not have a derivative at a point, it has jump discontinuity, a corner, a cusp, a vertical tangent, or removable discontinuity. The theorem, differentiability implies continuity. If it has a derivative at x equals c, then f is continuous at x equals c. Proof: if h equals 0, then f of c plus h equals f of c plus h minus f of c, which equals f of c plus h minus f of c all over h times h over 1. Now you take that as the limit h approaches 0. The limit h approaches 0 of f of c plus h equals the limit as h approaches 0 of f of c, which we just put it in there, and then plus your limit of h plus 0 of f of c plus h minus f of c all over h. Same thing, we put it in up to here. And multiply by your limit as h approaches 0 of h. Since our h goes to 0, that becomes 0. And this is just the definition of f prime of c. So f prime of c would equal f of c plus h minus f of c all over h. So we are left with the limit as h approaches 0 of f of c plus h equals f of c plus f of prime of c times 0. And anything times 0 is just 0. So we are left with limit as h approaches 0 for f of c plus h equals f of c.